Reality. We think we know what it is. The ground beneath our feet, the air we breathe, the world we see. But the deeper we look, the stranger it becomes. Did you know that what we perceive as solid matter is mostly space? The atoms that make up everything around us are 99.9% space. In addition, there is time. It's not a constant, ticking away in the background. Time can stretch, slow down, and even stop under the right conditions. So how much of what we experience is real, and how much is just a construct of our minds? What if the reality we trust is just a shadow of something deeper, stranger, and infinitely more complex? What is reality? For the first humans, the answer was simple. Reality was what they could see, hear, touch, and smell. The world around them was interpreted through their senses, guiding them through every day. The rustling of leaves signaled the approach of a predator. The distant crack of a branch indicated prey. And the sensation of warmth from a campfire chased away the cold night. This sensory reality was everything. Survival depended on it. Sight, hearing, touch, smell, these senses were the tools with which they cognized their environment. But for them, reality was limited to that which was accessible to direct perception. The invisible world beyond their senses was incomprehensible. Everything tangible became real. If a sound was heard, the danger was near. If an odor was smelled, food could be found. If something could not be smelled, it might not exist at all. Survival was a continuous process of interpreting these sensory cues, often in life or death situations. Recognizing the difference between the roar of a predator and the rustle of the wind could mean the difference between safety and death. Early humans lived in a world where reality was directly related to their immediate needs: food, shelter, protection. For them, reality was not questioned, it was lived through experience. However, as society evolved, the concept of reality also changed. The question of existence and meaning began to extend beyond the immediate environment. What lies beyond the senses? What forces shape the world? Over time, the limitations of direct perception have given way to imagination and conjecture. This curiosity led to the birth of new ideas, a reality that was no longer tied to the physical world. Early humans began to develop explanations for what they could not see or understand. Spirits, gods, and forces of nature became personifications of the unknown. Fire, lightning, and stars were attributed to forces beyond human control. Through mythology and beliefs, they created a wider reality that filled the gaps left by their sensory limitations. This cultural development marked a turning point in human thinking. Humanity's journey, which began with a simple need to survive, has now evolved into something much more complex. In one of the earliest philosophical explorations of reality, Plato presents this allegory of the cave. In this mental experiment, prisoners have been confined in a cave all their lives, seeing nothing but shadows projected on the wall in front of them. These shadows are all they know about. They mistake these flickering figures for reality itself. For them, the shadows are the only truth that they can perceive. But what if they broke free of their chains and turned around? What would they see? Plato's allegory suggests that human perception is often limited. What we perceive as reality may only be a shadow of a deeper, truer existence. The path to understanding true reality, Plato argued, begins with questioning the world as we perceive it. Plato's allegory is not just a philosophical exercise. It is a profound commentary on the limits of human perception. We may think we see the whole picture, but we're often limited by the limits of our senses and our experience. Reality can thus extend far beyond what we can directly observe. In the physical world, our understanding of reality underwent a significant change with the discovery of space-time. In the early 20th century, Albert Einstein shattered the age-old foundation of classical physics by showing that space and time are not separate entities, as previously thought, but are instead interwoven into a single four-dimensional fabric, space-time. According to Einstein's general theory of relativity, massive objects warp this fabric, creating what we experience as gravity. Planets revolve around the sun, not because they're pulled by some invisible force, but because the sun warps space-time around itself, creating a curved path for them. This revolutionary concept has completely changed our view of reality on a cosmic scale. Time, too, is no longer absolute. In Einstein's universe, time can be stretched or compressed, depending on the speed at which or its proximity to a more massive object. This idea, time dilation, means that time itself is relative, which changes our perception of how reality unfolds. The scientific method has for centuries allowed us to peel back the layers of this reality. Classical mechanics, developed by Newton, gave us the tools to understand the motion of objects by accurately predicting their trajectories. But as we began to delve deeper into the nature of the universe, discoveries, especially in quantum mechanics and relativity theory, showed us that reality operates in ways that had previously defied common sense. The search for the basic building blocks of reality began thousands of years ago. Back in the 5th century BC, the Greek philosopher Democritus suggested that everything in the universe consists of tiny, indivisible particles, atoms. These atoms, he argued, are the fundamental building blocks of all matter. This idea persisted for centuries until modern atomic theory took shape in the 19th century. Scientists such as John Dalton began to provide empirical evidence that all matter was indeed made up of atoms. These tiny particles, invisible to the naked eye, joined together in various ways to form everything from the air we breathe to the stars in the sky. Atoms were long thought to be the most fundamental, indivisible units of the physical world. But as our understanding deepened, we discovered that the atom itself could be broken down into even smaller particles. In the early 20th century, the discovery of subatomic particles, protons, neutrons, and electrons, showed that atoms were not indivisible after all. These subatomic components opened the door to a whole new field of physics, quantum mechanics. Quantum mechanics offered a radically different view of reality. At the atomic level, particles behave in ways that defy the rules of classical physics. Electrons don't just revolve around the nucleus in neat, predictable trajectories. Instead, they exist as probabilities. Their location not fixed until they are observed. This strange behavior introduces the concept of superposition. Particles can exist in multiple states simultaneously until they're measured. At this level, the very nature of reality itself becomes uncertain. Classical physics taught us that the universe works like a precise machine with predictable cause and effect relationships. But quantum mechanics has shown that reality, at its core, is governed by probabilities. This new understanding challenged the notion of a solid, deterministic universe and replaced it with one in which randomness and uncertainty reign. So, as our understanding of the atom deepened, it became clear that even protons and neutrons, the components of the atomic nucleus, are not the most fundamental units of matter. Within these particles, scientists have discovered quarks, elementary particles that come together in certain combinations to form protons and neutrons. Alongside them were particles called gluons, which are responsible for binding quarks together, acting as mediators of the strong force, the fundamental interaction that holds the atomic nucleus together. Quarks, however, are unlike anything else in the world of physics. They cannot exist individually, only in combinations, bound together by a strong force. This force is so powerful that trying to separate quarks results in more quarks. It is a strange and complex system that continues to challenge our understanding of the fundamental structure of matter. Subatomic physics, and especially the study of quarks and gluons, has pushed the boundaries of our knowledge, making it even more uncharted. Although the standard model of particle physics successfully explains many particles and forces in the universe, deeper questions remain. How do these particles interact at the most fundamental level? What are the true building blocks of reality? One of the boldest theories in the search for answers to these questions is string theory. This revolutionary idea suggests that the fundamental particles we observe, quarks, electrons, and others, are not point particles at all, but tiny one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to the different types of particles we observe. String theory is not limited to the redefinition of particles. It suggests that these strings exist not only in the familiar three dimensions of space and one dimension of time, but also in multiple dimensions, perhaps 10 or 11. These additional dimensions are beyond our immediate perception. They're coiled so tightly that they remain hidden from view. If string theory is correct, then reality may be far more intricate than we ever imagined, and extend into realms we've yet to observe. And this brings us to Copenhagen interpretation, one of the most famous philosophical foundations for understanding quantum mechanics. Proposed by physicist Niels Bohr, this interpretation is based on the idea that quantum particles do not possess certain properties until they are measured. Before observation, they exist only as probabilities. It's the act of measurement, the interaction with a conscious observer, that gives rise to reality. In other words, until you observe a particle, its state is fundamentally undefined, neither here nor there. However, not all physicists are satisfied with the Copenhagen interpretation. Some prefer the more radical, many worlds theory, first proposed by Hugh Everett. According to this interpretation, every time a quantum event occurs, every time a particle's wave function collapses, the universe splits. In one universe, the particle follows one path. In another, it follows a different path. Instead of converging to one outcome, all possible outcomes occur, but in different branching universes. These parallel worlds exist simultaneously, each representing a different version of reality. The theory of multiple worlds provides an alternative to the idea that observation leads to a so-called collapse of reality. Instead, it argues that all possible realities exist, but we're only aware of the one we live in. This is a striking concept. It expands the imagination and makes us think that reality is much more layered than we see in everyday life. Whether we adhere to the Copenhagen interpretation, the many worlds theory, or some other explanation, one thing is clear. At the quantum level, the rules of reality are not at all what they seem. Despite its elegance, however, string theory remains largely unproven. The theory operates on such small scales that modern technology can't yet test its predictions. Even with all of our advances in subatomic physics, there is still much we do not know. Quantum mechanics and general relativity, the two pillars of modern physics, are still incompatible with each other, especially when it comes to explaining gravity on the smallest scales. While the standard model describes known particles and forces, it fails to account for dark matter, dark energy, and a complete explanation of gravity, suggesting that there's much more to reality than we can perceive or measure. So the question arises, where are you now? Not in the physical sense or location, but in the sense of experience. Your consciousness is the lens through which reality is perceived. But what exactly is consciousness? Is it simply the result of electrical signals and chemical reactions in the brain? Or is it something more? A fundamental part of reality itself? For much of modern science, consciousness has been understood as a byproduct of the brain, an emergent property arising from the complexity of neurological processes, billions of neurons working in concert to form complex networks. generate everything we feel, think, and perceive. From this perspective, consciousness is simply what happens when the brain reaches a certain level of complexity. But this explanation does not fully solve the mystery. The hard problem of consciousness is how philosopher David Chambers put it, is the question of how and why subjective experience, a sense of awareness, arises from purely physical processes. Why should a particular arrangement of neurons produce a vivid inner world of visual images, sounds, emotions, and thoughts? The gap between the physical workings of the brain and the richness of conscious experience remains one of the most confusing questions in science and philosophy. Some argue that consciousness is not just a byproduct of matter, but something much more fundamental. Some theories suggest that consciousness may be woven into the very fabric of reality, much like space and time. This idea, known as panpsychism, asserts that consciousness is not limited to humans or animals, but is a basic property of all matter, pervading the universe to some degree. So, if consciousness is fundamental, it could mean that the universe itself has consciousness to some extent. This shifts the question from how does the brain produce consciousness to how does consciousness manifest itself through matter? This in turn suggests that the distinction between mind and matter may be artificial, that consciousness and the material world are deeply interconnected. Other theories offer a more traditional approach. Consciousness is an emergent property. According to this view, the complexity of the brain creates consciousness in the same way that water emerges from individual hydrogen and oxygen molecules. In this view, consciousness is completely dependent on the physical structure of the brain. When the brain ceases to function, consciousness disappears. But this explanation still leaves unanswered the fundamental riddle of subjective experience. Philosophers and scientists have debated the true nature of consciousness for centuries. Is it reducible to material processes? Or is it something more, something that perhaps eludes our current understanding of physics and biology? If consciousness plays a role in shaping what we perceive as reality, could it be that our subjective experience is not just a reflection of reality, but part of its very foundation? Ultimately, the nature of consciousness remains one of the greatest mysteries. What is it about consciousness that distinguishes it from everything else in the universe? Is consciousness a window into a deeper level of reality, or just a byproduct of complex physical systems? The question of where you are, where consciousness fits into the grand plot of existence, remains an open question. The more we learn about the brain and the universe, the clearer it becomes that reality may be far more intricate than we can currently comprehend. Perhaps one day, discoveries will show that consciousness is not just something happening inside reality, but a fundamental key to understanding reality itself. For centuries, we've gazed into the night sky, listening to the stories told by the light of the distant stars. We've built telescopes to see deeper and farther, to uncover the secrets hidden within the cosmos. But light is only part of the story. There is another, more subtle language that the universe speaks. A language of ripples and echoes written into the very fabric of space and time. Welcome to the era of gravitational wave astronomy. Gravitational waves are ripples in the fabric of space-time, predicted over a century ago by Albert Einstein. Unlike electromagnetic waves, such as light, radio, or X-rays, which are vibrations of electric and magnetic fields, gravitational waves are distortions in the very structure of space and time itself. They're created by some of the most violent and energetic events in the universe. Einstein's general theory of relativity, published in 1915, proposed that massive objects like stars and planets don't simply exist in space, they warp and curve it. This distortion is what we perceive as gravity. But Einstein went further. He suggested that when these massive objects accelerate, when they move, collide, or explode, they create ripples in space-time. Much like a stone thrown into a pond creates ripples on the water's surface. Gravitational waves are produced by cataclysmic events, collisions of black holes, explosions of supernovae, the merging of neutron stars. These waves travel across the universe at the speed of light, carrying with them information about the events that created them. They tell us about the nature of gravity, the properties of black holes, and the birth of stars. But gravitational waves are incredibly weak by the time they reach us. Having traveled billions of light years across space, detecting them requires instruments of unprecedented sensitivity, machines capable of measuring changes of distance smaller than a fraction of the width of a proton. This is the challenge that scientists have faced for decades. In the 1990s, a new generation of scientists set out to build such an instrument. The result was LIGO, the Laser Interferometer Gravitational Wave Observatory. It consists of two massive detectors, one in Washington and the other in Louisiana, that are designed to detect these faint ripples in space-time. Their construction marked the beginning of a new era in the search for gravitational waves. Gravitational waves don't just pass through the vast reaches of space, they also pass through us. As these waves travel across the universe, they stretch and squeeze the space they move through, causing distances between objects to change. But the question arises, do gravitational waves stretch us too? In theory, yes. Gravitational waves do stretch and compress everything in their path, including us. However, the effect is incredibly tiny. A passing gravitational wave would stretch you by less than the width of an atomic nucleus. It's so small that it can't be felt or noticed by us in any way. At LIGO, the world's most precise measuring device, a laser interferometer is used to detect these minuscule changes. The device splits a laser beam and sends the two halves down perpendicular arms, each several kilometers long. When a gravitational wave passes by, it changes the length of these arms by a tiny amount, altering the interference patterns of the light. This change indicates that a gravitational wave has passed. Thus, while gravitational waves do indeed stretch us, their effects are so minute they can only be detected by the most advanced technology, like the instruments at LIGO. Through these ultra-precise measurements, we're able to hear the faint whispers of the universe. Gravitational waves are not just distortions in space-time. They also carry energy. When massive objects like black holes merge, they release an enormous amount of energy in the form of gravitational waves. This energy travels across the cosmos, rippling through space-time and revealing the most powerful events in the universe. The first detection by LIGO in 2015 confirmed that these waves carry energy away from their source, causing the black holes to spiral towards each other and eventually merge. The amount of energy carried by these waves is staggering. In just a fraction of a second, the merging black holes emitted more energy than all the stars in the observable universe combined. This discovery not only confirmed Einstein's theory, but also opened a new way to understand the most energetic processes in the universe, revealing information about the objects and events that created these waves. Each detection tells a story of the formation and evolution of black holes, neutron stars, and even entire galaxies. The energy carried by gravitational waves does more than just stretch space. It allows us to map the universe's most extreme environments, to understand how black holes and neutron stars form, and to explore the very nature of space and time. Gravitational waves not only affect the space they move through, they also have profound effects on the very objects that create them. When two massive objects like black holes merge, the gravitational waves they emit carry away significant amounts of energy. This loss of energy directly impacts the motion and structure of the black holes themselves. When neutron stars collide, the effects are even more dramatic. Gravitational waves not only strip away energy but also determine the final outcome of the collision. Whether a new, more massive neutron star is formed, or whether the stars collapse into a black hole. These waves provide clues about the internal structure and composition of these dense, enigmatic objects. The gravitational waves we detect are signals from the heart of cosmic violence, revealing the forces at play, the incredible energies involved, and the final fate of these cosmic giants. They help us understand how stars live and die, how black holes are born, and how matter behaves in the most extreme environments imaginable. To detect gravitational waves, scientists needed to build an instrument unlike any other: the Laser Interferometer Gravitational Wave Observatory, or LIGO. Its design is based on a simple but powerful idea: using light to measure the tiniest distortions in space. The principle behind LIGO is simple in concept, but complex in execution. A powerful laser beam is split into two, sending the light down two long arms, each 4 kilometers in length. At the end of each arm, mirrors reflect the light back to the central beam splitter, where the two beams are recombined. In the absence of a gravitational wave, the beams cancel each other out perfectly due to their carefully calibrated paths. However, when a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction. This changes the length of the arms, altering the time it takes for the laser beams to return, creating a distinctive interference pattern that LIGO's detectors can measure. To detect these incredibly small changes, LIGO must operate under extreme conditions. The entire interferometer is housed in ultra-high vacuum tubes to eliminate air molecules that could scatter the laser light. The mirrors are suspended by finely tuned systems that isolate them from ground vibrations caused by traffic, wind, or distant earthquakes. LIGO is not alone in its quest to detect gravitational waves. Across the globe, a network of observatories works together to listen to the universe, combining their data to improve the precision and reliability of detections. Virgo, located near Pisa, Italy, is LIGO's European counterpart. With its 3-kilometer-long arms, Virgo uses the same principles of laser interferometry to detect gravitational waves. By collaborating with LIGO, Virgo helps pinpoint the location of cosmic events, allowing astronomers to direct their telescopes to the right portion of the sky at the right time. In Japan, the Kagra Observatory brings new innovations to the field. Located deep underground to shield it from surface noise, Kagra also uses cryogenically cooled mirrors to reduce thermal vibrations, making it even more sensitive to gravitational waves. By combining data from detectors on different continents, we can determine the location of gravitational wave sources with much greater accuracy. When a gravitational wave passes through Earth, it arrives at each observatory at slightly different times. By measuring these time differences, we can pinpoint the source of the waves in the sky. This global network has enabled us to conduct multi-messenger astronomy, where gravitational waves are observed alongside light, radio waves, and gamma rays. Together, they paint a fuller picture of the most extreme cosmic events. Gravitational wave astronomy is truly a global effort. Scientists from every corner of the world are working together to unlock the universe's secrets, proving that in science, collaboration knows no borders. Gravitational waves come in a wide range of frequencies, and each frequency reveals a different story about the universe. LIGO and its partner observatories are tuned to capture specific frequencies that align with some of the most energetic events in the cosmos. LIGO is designed to detect gravitational waves in the frequency range of approximately 10 Hz to 10,000 Hz. This range is well suited for capturing waves produced by events like the merging of stellar mass black holes or the collisions of neutron stars. These frequencies fall within a range similar to that of human hearing, but instead of sound waves traveling through air, they are ripples traveling through space-time. Each gravitational wave signal can tell us about the objects that created it. For example, a merger of two black holes produces a chirp, a wave pattern that increases in frequency and amplitude as the black holes spiral closer together, culminating in a sudden peak as they merge. The unique signature of each chirp allows scientists to determine the masses, spins, and distances of the merging objects. However, not all gravitational waves fall within LIGO's detection range. Lower frequency waves, such as those produced by the mergers of supermassive black holes found in the centers of galaxies, lie outside LIGO's current capabilities. Detecting these lower frequency waves requires different types of instruments. And this is where the future of gravitational wave astronomy comes into play. The planned Laser Interferometer Space Antenna, or LISA, will be positioned in space to detect these lower frequency gravitational waves. By expanding our observational range, LISA will allow us to hear the deep, slow rumblings of supermassive black hole mergers and other cosmic phenomena to further extend our understanding of the universe. By broadening the range of detectable frequencies, we'll open up new windows into the universe, enabling discoveries from high-pitched chirps of merging neutron stars to the low-frequency growls of supermassive black holes colliding. Each new frequency band brings with it new opportunities for understanding the cosmos. In August 2017, a groundbreaking moment in astronomy took place. For the first time in history, an astronomical event was observed in both gravitational waves and electromagnetic radiation. This event, known as GW 170-817, marked the dawn of multi-messenger astronomy. GW 170-817 was the merger of two neutron stars, the remnants of massive stars that had previously exploded as supernovae. As these neutron stars spiraled together, they emitted gravitational waves detected by LIGO and Virgo. Just 1.7 seconds later, NASA's Fermi Gamma Ray Space Telescope observed a burst of gamma rays, pinpointing the event's location in the sky. This unique observation triggered an unprecedented global effort. Within hours, dozens of telescopes across the planet began observing the region in different wavelengths, from radio to X-rays, allowing scientists to study the event in detail like never before. This first-ever joint observation provided critical insights into the universe's workings. It confirmed that neutron star mergers are key sites for producing heavy elements. such as gold and platinum, and scattering them throughout the cosmos. This was a long-suspected theory, now proven with direct evidence from gravitational waves. The discovery of GW 17817 demonstrated the immense power of combining gravitational wave and electromagnetic observations, allowing us to witness cosmic events with greater clarity and precision. It opened a new window into the universe, where every detection tells a deeper, richer story. Multi-messenger astronomy represents a new era of discovery, where light and gravitational waves together illuminate some of the most profound mysteries of the cosmos. Gravitational wave astronomy is still in its infancy, but its potential is vast. What could we uncover in the coming years and decades? What new mysteries of the cosmos might we solve? With more sensitive detectors and more powerful instruments, we might soon detect gravitational waves from sources we've never observed before. Could we hear the faint echoes of the Big Bang, confirming theories about the earliest moments of the universe? Detecting these primordial waves could provide direct evidence of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. It could answer questions about the fundamental forces that shape the cosmos. Gravitational wave astronomy could also reveal unknown phenomena, objects or events that we've never imagined, exotic forms of matter, hidden dimensions, or the mysterious dark matter that makes up most of the universe's mass. Gravitational waves could help uncover these elusive secrets. We're standing at the edge of discovery, poised to answer some of the most profound questions ever asked about our universe. Gravitational wave astronomy offers a new way to explore the cosmos, opening a path to discoveries beyond our wildest dreams. The universe is full of whispers, and we are just beginning to listen. Imagine a burst of energy so powerful that it eclipsed an entire galaxy for a moment. A burst of unimaginable power that traveled billions of light years to reach us, whose origin is still shrouded in mystery. It's not simply some sort of science fiction. It's the true story of gamma-ray bursts, the most energetic events known in the universe. On October 9th, 2022, astronomers discovered something unprecedented, the brightest gamma-ray burst of all time, which they nicknamed BOAT. It was so unusual that it shook nearly all of their previous concepts about these cosmic phenomena. But the story of GRB 2210-09A is not just about brightness, it's about the questions it raises, anomalies in its spectrum, the unexpected absence of heavy elements, and new challenges to our understanding of how the most powerful explosions in the universe happen. What caused this colossal explosion? And what secrets can it reveal about the forces shaping our universe? The universe is a realm of unusual phenomena, some of which challenge the very limits of our understanding. Prominent among them are gamma-ray bursts, GRBs, some of the most powerful and mysterious explosions known to science. Discovered quite by accident in 1967 by U.S. military satellites, gamma-ray bursts were at first a puzzling mystery and cause for concern because of their intense energy release, which were mistaken for nuclear testing. However, as it became clear that their origin was from somewhere in the cosmos, GRBs quickly evolved from being a top-secret mystery to one of the most studied astrophysical phenomena. These bursts are divided into two main types: short GRBs, which last less than 2 seconds, and long GRBs, which can last up to several minutes. This division is not merely academic. It reflects the different underlying physical processes. Short GRBs are usually associated with neutron star collisions. while long GRBs, like the one observed in October 2022, are associated with a cataclysmic collapse of massive stars. The event in question, dubbed brightest of all time, or BOAT, occurred in the constellation Sagitta. Detected on October 9, 2022, this gamma-ray burst was unlike anything astronomers had ever before observed. Its brightness, 10 times greater than all previously recorded GRBs, shocked the scientific community. What made this event even more amazing was its duration. It lasted 10 minutes, and the afterglow was visible for more than 10 hours. Most outbursts disappear from view within a few seconds or minutes, making BOAT an exceptional event. But beyond the spectacle, the BOAT event has profound implications for our understanding of the universe. Gamma-ray bursts are, by their very nature, windows into extreme conditions that cannot be replicated on Earth. They allow scientists to investigate the fundamental laws of physics, especially when matter is subjected to intense energy and gravitational forces. The BOAT event, so bright and so close, provided a unique opportunity to study these extreme conditions in unprecedented detail. The resulting data opens new avenues for understanding not only gamma-ray bursts, but also the very processes that govern the life and death of stars. The brightest of all time, GRB 221009A, then stood out not only for its staggering intensity, but also for its amazing duration. The explosion was so powerful that it was the brightest gamma-ray burst ever recorded, lasted 10 minutes, and left an afterglow visible for more than 10 hours. Such an event at a distance of only 2.4 billion light-years is not just rare, it's almost unprecedented, occurring only once every 10,000 years. What makes this outburst truly unique is the combination of extreme brightness and prolonged visibility. Most GRBs are fleeting, often only detectable for a few seconds or minutes. In contrast, GRB 221009A lasted much longer. High-energy emissions lasted for tens of thousands of seconds. This duration provided an unprecedented opportunity for observations and analysis over a wide wavelength spectrum, from X-rays to gamma rays. The BOAT brightness was so intense that it caused saturation effects in numerous scientific instruments, including the GBM, Gamma Burst Monitor, and LAT, Large Area Telescope. These instruments, designed to capture and analyze high-energy photons, were overwhelmed by the power of the event, resulting in significant noise and data delays. Notably, the 400 GeV, giga-electron-volt photon, was detected nearly 10 hours after the initial burst, indicating unusually high energy levels. Despite its stunning brightness and duration, this event also presented us with significant challenges. Spectral analysis showed that the peak energy of the flare reached about 15 MeV, mega-electron volts, at the very beginning of the event, gradually decreasing over time. However, part of what puzzled scientists was the discovery of a BOAT-related supernova, which turned out to be surprisingly ordinary. Given the extreme nature of the GRB, one might expect its progenitor supernova to be equally extraordinary. Instead, the detected supernova turned out to be almost completely unremarkable. It even lacked signs of heavy elements, which are usually associated with such powerful explosions. But more on that later. This unexpected discovery has led to several hypotheses, one of which suggests that the relative position of the Earth to the GRB may have played a crucial role in the concentrated detection of gamma rays. The narrow jets emitted during the explosion were likely pointed almost perfectly toward Earth, making the event appear much more intense than if the jets were slightly off-axis. This alignment, combined with the GRB's power, created the perfect storm that resulted in BOAT being recorded as the brightest GRB ever observed. In addition, the detection of such high-energy photons raises intriguing questions about the mechanisms of radiation. conventional models can't fully explain the observed unusual energy levels, leading some researchers to consider the possibility of new physics, such as interactions with dark matter particles. While these ideas remain speculative, they highlight the potential of GRB 221009A to expand our understanding of the universe in directions we have yet to fully comprehend. The formation of gamma-ray bursts is closely intertwined with the life cycle of massive stars. When a star, several times the mass of the Sun, exhausts its nuclear fuel, its core can no longer support the weight of the outer layers. This catastrophic collapse leads to a supernova explosion. But in some stars, it also leads to the formation of an incredibly dense black hole. When matter from a collapsing star falls into a black hole, strong magnetic fields turn some of that matter into narrow, focused jets that fly outward at nearly the speed of light. These jets are the engines of gamma-ray bursts, and their orientation relative to the Earth determines whether we can observe GRBs. In the case of the boat event, the jets were particularly narrow and pointed almost directly at Earth. Normally, GRB jets scatter somewhat as they pass through space, but in the boat event, the jets remained exceptionally concentrated, focusing their enormous energy into a relatively smaller area, resulting in a more intense emission. The influence of these jets extends far beyond the place of their origin. When 221009A erupted, its intense gamma rays reached the Earth and interacted with our planet's atmosphere in surprising ways. One of the most significant effects was a temporary compression of the Earth's ionosphere, a layer of the atmosphere containing a high concentration of ions and free electrons. This compression was akin to the effect caused by a large solar flare when the ionosphere is bombarded by solar particles, causing communication systems and satellites to malfunction. However, the gamma rays from the boat event were much more energetic than those normally associated with solar flares. The energy of the burst was enough to cause noticeable changes in the ionosphere, even at altitudes where such interactions rarely occur. Observatories around the world quickly detected these changes, leading to a flurry of data analysis to understand the full impact of the GRB on Earth's atmosphere. The data collected during this event has given scientists new insights into how such bursts can affect planetary atmospheres, especially the interaction of high-energy photons and their potential to affect atmospheric chemistry and dynamics. At the chemical level, gamma rays triggered reactions in the atmosphere that produced additional nitrogen oxide and other reactive nitrogen species. These molecules play a critical role in ozone chemistry, particularly in the destruction of ozone in the upper atmosphere. Although the exact effect both had on global ozone levels hasn't yet been studied, such bursts may contribute to local or temporary changes in ozone concentration, potentially affecting the protection of the atmosphere from harmful ultraviolet radiation. However, these observations have also raised new questions. The unprecedented strength and narrowness of the boat event jets challenge existing models of GRB formation and propagation. Standard models predict a certain degree of jet spread, which helps disperse energy over a wider area. But the boat event jets have disproved these expectations, suggesting that under certain conditions, jets can remain tightly focused over much greater distances than previously thought. According to modern ideas, the extreme energy and rapid rotation of the collapsing star played a key role in this. The intense magnetic fields produced by the star's rotation probably contributed to the collimation of the jets, preventing them from spreading out in space. In addition, the lack of significant interference from surrounding matter may have allowed the jets to maintain their tight focus over vast distances. These findings not only challenge our current models, but also hint at the possibility of previously undetected GRBs with similarly focused jets that may have been missed by our instruments due to their directional nature. A better understanding of these mechanisms may reveal new classes of GRBs and their potential impact on both the local environment and distant planets. including Earth. However, let's return to the question of how our outburst is related to the formation of elements in the universe. It's simple. The formation of elements in the universe is history written in the hearts of stars. Inside a star, nuclear fusion works like a cosmic forge, turning light elements, such as hydrogen and helium, into increasingly heavier elements. This process continues until the element iron is formed. At this point, the fusion process no longer releases energy. It requires more energy than it produces, leading to a catastrophic imbalance. The star can no longer support its weight, leading to its eventual collapse, and often to a supernova explosion. While fusion in stars easily produces elements up to iron, much more extreme conditions are required to create elements heavier than iron, such as gold. These heavier elements are formed primarily by a process known as fast neutron capture, or R process. During the R process, the dense environment with a high neutron flux allows atomic nuclei to rapidly capture neutrons, creating increasingly heavier elements in a very short time. This process is best known in neutron-star collisions, where the enormous energy and neutron-rich environment create ideal conditions for the R process to occur. However, neutron-star collisions are not the only cosmic events that can produce heavy elements. Another potential site for R process nucleosynthesis is the collapse of massive, rapidly rotating stars into black holes, events known as collapsars. In these scenarios, intense magnetic fields and rapid rotation can drive powerful jets that contribute to the R process, potentially creating significant amounts of heavy elements such as gold and platinum. But when scientists pointed their instruments at the boat event, they were surprised to note something conspicuously missing. Despite the extreme energy and conditions seemingly ripe for nucleosynthesis in the R process, no evidence of heavy elements was detected in the supernova spectrum. No gold, no platinum, none of the things one would expect from such a powerful event. This absence raises important questions about our understanding of how and where the heaviest elements in the universe are formed. This surprising result leads to the thought that not all collapsars are prolific producers of heavy elements. Perhaps the conditions required for significant nucleosynthesis in the R process are even more specific than we thought, and may only occur under certain conditions within these already rare events. On the other hand, this could mean that other processes or conditions related to neutron-star mergers play a more significant role in enriching the universe with heavy elements. Another interesting thing about Brightest of All Time is that it may well shed some light on the nature of dark matter. According to one intriguing hypothesis, dark matter may consist of particles called axions, hypothetical particles that have not yet been directly observed. The idea that photons, particles of light, can turn into axions as they travel through space is a tantalizing one. If true, it could help explain why dark matter is so hard to detect. Perhaps it's hiding in plain sight in the form of photons that can turn into axions and elude our instruments. The boat event, with its intense burst of gamma rays, provides a unique opportunity to explore this hypothesis. As these gamma rays spread across the vastness of space, some of them may have interacted with cosmic magnetic fields, becoming axions. This process could reduce the flux of gamma rays reaching Earth, a subtle signal that could hint at the presence of axions. Although no definitive evidence for the existence of axions was found in the boat event data, this possibility remains an interesting avenue for further research. If future observations of such events reveal patterns consistent with the conversion of photons into axions, this could be a breakthrough in our understanding of dark matter and open the door to new physics beyond the standard model. As we look to the future of astrophysics, the study of gamma-ray bursts remains a cutting-edge frontier full of promise and mystery. Current missions such as NASA's Fermi Gamma Ray Space Telescope and the European Space Agency's Integral continue to play a critical role in directing and analyzing GRBs. But the next generation of missions will push these boundaries even further. Projects such as the Sino-French SVOM mission and NASA's upcoming COSY mission are designed to provide unprecedented insight into the high-energy universe. These missions will aim to detect the most extreme cosmic events and will allow us to collect data with greater precision, potentially unlocking new physics and deepening our understanding of the mechanisms behind these powerful explosions. Will future observations reveal the elusive nature of axions, or perhaps identify the specific conditions under which the heaviest elements are formed? These are the questions that define the next steps in the exploration of the universe, guiding us toward a deeper understanding of the cosmos and our place in it. Events such as BOAT serve as milestones in the development of astrophysics, reminding us that the universe is much more complex and dynamic than we can currently understand. Each discovery forces us to ask new questions and propels our quest for knowledge forward. And who knows, perhaps the answers to these mysteries are just a cosmic explosion away and are waiting to be uncovered by curious minds. In the meantime, we'll continue to keep you up to date with new developments. Stay inquisitive, and until next time, surely you've heard by now that black holes can be so massive that they can outshine entire galaxies. But some of them are quite mobile, so much so that they roam the Milky Way like cosmic ghosts, undetectable. Of course, you may be confused or even mesmerized by the fact that the nearest black hole to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints. Frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a far more complex way than we ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we're familiar with small black holes, the remnants of dying stars and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the ball cluster closest to Earth. What he discovered was nothing short of groundbreaking: a black hole with a mass about 800 times the mass of our Sun. This celestial object is somewhere between 6,000 and 7,200 light-years away from us. Why is this so important, you ask? Well, for years, astronomers have struggled with a gap in the black hole genealogical tree. We've had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But black holes of intermediate mass turned out to be a missing link, mysterious relatives about which everyone has heard but no one has met. An equally interesting question is how these black holes of intermediate mass form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when they merged into larger galaxies. Another theory states that they could have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played an important role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass. It's like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may be key players in the formation of galaxies and may even hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,855 miles away, our nearest neighboring black hole, Gaia BH1, is thousands of light years away from Earth. But what does that proximity mean in the context of black holes? And why is this proximity important? In 2020, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it's a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened up new possibilities for studying stellar evolution and interactions. After the ejection of HR 6819, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. The main task of Gaia is to map the Milky Way in unprecedented detail, and it was thanks to this painstaking work that Gaia BH1 was discovered. As the closest known black hole to Earth, Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements and may help answer fundamental questions about the properties of black holes, such as mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more accurately these instruments will be able to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public imagination. It makes the cosmic more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the centers of galaxies or double star systems. But what happens when a black hole is left to roam the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue? And how do astronomers even manage to find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first ever unambiguous discovery of a wandering black hole. Located 5,000 light-years away from Earth, this black hole weighs 7.1 times the mass of our Sun and moves at a staggering speed of about 28 miles per second. The key to this revolutionary discovery lies in a phenomena predicted by Einstein's general theory of relativity, known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light of that star. This creates a brief brightening phenomenon, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. And this is how our newly discovered wandering black hole likely began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole is traveling. Its speed is about 28 miles per second, which is a very large value relative to the nearest stars. This speed is likely the result of the very impact of a dying massive star sending it on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions, such as the European Space Agency's Gaia telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more such space travelers. These future discoveries will not only increase the number of known rogue black holes, but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled over the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other, even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency, where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or its central black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to hit the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas toward the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slower, and if it's too small, it catches up due to the abundance of gas and dust in the galaxy. So some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops, and they turn into red nuggets, still retaining their huge black holes. As we move farther into the black hole abyss, it becomes apparent that young, gas-rich galaxies serve as the birthplace of various black hole phenomena. Whether they're luminous black holes or intermediate mass, wandering black holes hurtling through space, or the nearest black holes to Earth, their origins can often be traced back to these bright, young galaxies. Understanding the cradle of these cosmic giants helps us unlock the mysteries that black holes hold. Now, let's look at something really rare. There is a situation where black holes collide. In doing so, they create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory, in 2015 opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, thereby testing our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects that reveal a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond or linear pond, the throw of a stone creates an isolated ripple. In a stormy sea or nonlinear, however, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or chirps. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem. These colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merged to form larger galaxies, like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we travel deeper into the abyss of black holes, we discover that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. And of course, each discovery, from the frequencies they generate to the nature of gravity itself, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models become more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal? Imagine a particle so elusive that trillions pass through you every second but leave no trace. A particle born in the fiery hearts of stars, in the cataclysmic collapse of supernovae, or perhaps in the first moments of the universe itself. These are neutrinos, tiny messengers from space, carrying secrets that could rewrite the laws of physics. But why are they so hard to detect? And what secrets can they reveal if we finally learn to listen to their whispers? Diving into the realm of these ghostly particles, we go where the known meets the unknown, and where the smallest particles hold the key to the biggest questions. The neutrino story begins in the early 1930s, when the study of particle physics was undergoing a revolutionary transformation. It was a time when the universe was revealing its secrets to those who dared to explore its mysteries. Wolfgang Pauli, an Austrian theoretical physicist, faced a problem. In beta decay, a type of radioactive decay observed in atomic nuclei, energy seemed to disappear. This disappearance contradicted the principle of conservation of energy, one of the most fundamental laws of physics. Pauli proposed a radical idea. What if the missing energy was carried away by an undetectable particle? He tentatively named this particle neutron, although Enrico Fermi soon renamed it neutrino to avoid confusion with the already discovered neutron. Fermi, an Italian physicist, was in turn instrumental in developing a theory describing this elusive particle and cementing its place in the scientific lexicon. Let's travel back to the Cold War era, a time when science and politics were closely intertwined. Neutrinos, once a mere theoretical curiosity, became the center of secret research projects driven by geopolitical tensions. The rivalry between the United States and the Soviet Union was not just about military might. It extended to the realm of science, where both sides sought breakthroughs that could give them an advantage. One such story is that of Bruno Pontecorvo, an Italian physicist who fled to the Soviet Union amid growing political tensions in the West. Pontecorvo had been heavily involved in neutrino research, and his defection caused a stir in both intelligence services and scientific circles. His departure led many to wonder if crucial information had been compromised, illustrating the distrust and anxiety of the Cold War era and the extent to which neutrino research had become the subject of international intrigue. This period was marked by secret experiments, some conducted deep underground in abandoned mines or remote locations, where scientists were trying to catch these ghostly particles. Neutrinos, while among the most common particles in the universe, are also among the most elusive. These tiny particles are incredibly light and have such a small mass that for a long time it was thought to be zero. Unlike other fundamental particles, neutrinos interact only through the weak nuclear force and gravity, making them extremely difficult to detect. They pass through ordinary matter as if it were not there. Trillions are passing through you right now, completely undetected. 3 types or flavors of neutrinos are known: electron, muon, and tau neutrinos. Each is associated with a corresponding charged particle: electron, muon, and tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, known as neutrino oscillation, was a revolutionary discovery because it suggested that neutrinos have mass, a fact not accounted for in the original standard model of particle physics. Neutrino oscillation occurs because neutrinos exist in a quantum superposition of different mass states. When a neutrino travels through space, it can move between these mass states, resulting in a change in flavor. This discovery not only won the 2015 Nobel Prize in Physics, but also pointed out gaps in the standard model, changing our understanding of fundamental physics. Neutrinos are also key players in some of the most dramatic processes in the universe. At the heart of a star, nuclear reactions generate huge numbers of neutrinos, which then leave the star almost instantaneously, taking energy with them. Neutrinos are the first particles to fly out of a dying star, signaling the start of a supernova. These particles provide crucial information about the processes taking place in the core, long before the light can escape. When a massive star reaches the end of its life cycle, its core collapses, leading to a supernova explosion. During this cataclysmic explosion, an enormous number of neutrinos are produced, orders of magnitude greater than the energy emitted by light. These neutrinos leave the supernova almost instantly, spreading through space, and some of them eventually reach Earth, giving a glimpse into these distant, violent events. There's also speculation that neutrinos may be linked to one of astrophysics' biggest mysteries: dark matter. Some theories suggest that a type of neutrino, perhaps a sterile neutrino, that does not interact with any known fundamental force other than gravity, may make up dark matter, the invisible mass that makes up most of the universe's matter. Although this remains an area of intense research, the possibility that neutrinos could unlock the secrets of dark matter emphasizes their importance to our quest to understand the cosmos. So the hunt for high-energy neutrinos has taken scientists to some of the most extreme places on Earth. Deep in the ice of Antarctica stands the Ice Cube Neutrino Observatory, scanning the cosmos for these elusive particles. Neutrinos, especially at extremely high energies, are the messengers of some of the most violent events in the universe, events that are still cloaked in mystery. Recent research has begun to peel back the layers of this mystery, pointing to active galactic nuclei, or AGNs, as significant sources of these high-energy neutrinos. AGNs are the luminous centers of galaxies powered by supermassive black holes. When matter falls into these black holes, it releases huge amounts of energy, often forming jets of high-speed particles. However, recent discoveries show that these jets may not be the only source of neutrinos. In 2022, the galaxy NGC 1068 was identified as a likely source of high-energy neutrinos, a discovery that surprised many in the scientific community. The neutrinos were traced to the galaxy's core, where a supermassive black hole is hidden behind thick layers of dust and gas. This discovery disproved the popular belief that such neutrinos can only be emitted by galaxies with bright jets, such as blazars. The surprises didn't end with NGC 1068. Further studies revealed two more galaxies, NGC 4151 and NGC 3079, as potential sources of high-energy neutrinos. The findings strongly suggest that the environment around supermassive black holes and these active galaxies is a powerful neutrino factory. These findings have led to a paradigm shift in our understanding of where high-energy neutrinos come from. As the search for these cosmic messengers intensifies, so does the competition between the world's most advanced neutrino detectors. IceCube has already made remarkable discoveries, but other projects are on the horizon that aim to push the boundaries of our knowledge even further. In Japan, the Hyper Kamiokande is poised to become a leader in neutrino detection. This huge underground detector, located in a cave specially dug for the purpose, will be filled with 260,000 tons of ultraviolet water. The goal is to capture fleeting flashes of Cherenkov radiation produced when neutrinos interact with water molecules, a technique honed over decades of Japanese research. Meanwhile, in the US, the Deep Underground Neutrino Experiment, also known as DUNE, is being built in an old gold mine in South Dakota. Unlike Hyper-K, which uses water, DUNE will utilize a state-of-the-art time projection camera in liquid argon. This technology promises to capture neutrino interactions with unprecedented precision, allowing scientists to map neutrino properties in great detail. Although both the Hyper Kamiokande and DUNE share the common goal of solving the mysteries of neutrinos, their approaches differ significantly. Hyper-K is based on proven technologies and aims at mass data collection. DUNE, on the other hand, relies on innovative technologies that can reveal new aspects of neutrino behavior. The stakes are high. Both projects seek to answer fundamental questions about the universe, such as the origin of matter itself. One of the key areas of research will be a phenomenon known as charge parity violation, which may explain why the universe is composed mainly of matter rather than antimatter. Charge parity violation, CP violation, could be the key to solving this cosmic mystery, and Hyper-K and DUNE are designed to find it. By comparing the oscillations of neutrinos and their antimatter, antineutrinos, as they pass through space, these detectors can show whether there's a fundamental difference in the behavior of matter and antimatter. But the race to find CP violation is also a race against time. Hyper Kamiokande is expected to begin collecting data as early as 2027, which could give it an edge over DUNE, which is not expected to be fully operational until the early 2030s. The competition between these two experiments could determine the future of neutrino physics for decades to come. The Standard Model of particle physics has long been considered one of the most successful theories in science, providing a framework for describing the fundamental particles and forces that make up the universe. However, even this robust model has its limitations, and nowhere is this more apparent than in the study of neutrinos. These elusive particles, which have almost no interaction with other matter, have properties that push the boundaries of our understanding. One of the most serious challenges to the Standard Model comes from the discovery that neutrinos have mass. According to the original scheme, neutrinos were thought to be massless, but the observation of neutrino oscillation, when neutrinos change from one type to another, proved otherwise. This discovery alone was enough to shake the foundations of the Standard Model. But that was not all. The consequences of the appearance of neutrino mass go beyond a simple revision of the model. They suggest the possible existence of a new type of neutrino, the sterile neutrino. Now, we've already mentioned this in passing, but here's the gist of it. Unlike the three known types of neutrinos, electron, muon, and tau, which interact through the weak nuclear force, sterile neutrinos interact only through gravity. This makes them even more difficult to detect, but their existence may well explain several mysteries in physics. If sterile neutrinos are shown to exist, they'd not only call into question the completeness of the standard model, but would open the door to entirely new physics. This would require extending the model to include these new particles, potentially leading to a more unified theory of the fundamental forces. Neutrinos may also provide clues to another profound mystery: the scarcity of antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. But today we observe a universe in which matter predominates and antimatter is rare. This imbalance is one of the great mysteries of cosmology. One theory suggests that neutrinos and their antimatter, antineutrinos, may behave differently. If neutrinos do break this symmetry, this could later explain why there is more matter than antimatter left after the Big Bang. The T2K experiment in Japan has provided tantalizing evidence for CP violation in neutrinos. In this experiment, beams of neutrinos and antineutrinos are sent on a 185-mile, 300-kilometer journey across Japan to the Super Kamiokande detector. For nearly a decade, researchers have noticed that neutrinos oscillate into different types more often than antineutrinos, suggesting that they may indeed behave differently. This potential CP violation in neutrinos could be the missing piece to explain why the universe is made up mostly of matter. However, the current results, while promising, are not yet conclusive. The level of statistical significance required to recognize a discovery in particle physics is 5 sigma. The T2K results have only reached about 3 sigma, and this means that although the evidence is strong, it's not absolute. To truly confirm the CP violation in neutrinos and unlock the secrets of antimatter rarity, scientists are turning to the next generation of neutrino detectors. Hyper-K in Japan and Dune in the US are poised to take this research to the next level. These massive detectors will collect many times more data with greater accuracy, potentially reaching the 5 sigma threshold. If these experiments confirm CP violation in neutrinos, it could revolutionize our understanding of the origin of the universe and answer one of the most persistent questions in science: why there is something rather than nothing. The study of neutrinos, once considered an obscure branch of physics, may ultimately hold the key to understanding the very fabric of our reality. To answer some of physics' deepest questions, scientists are developing the next generation of detectors, each more advanced than the last. One of the most ambitious projects in this field is the Karlsruhe Tritium Neutrino Experiment, or CATRIN, in Germany. The CATRIN project has one goal: to measure the mass of neutrinos. The experiment aims to observe the beta decay of tritium, a radioactive isotope of hydrogen, to determine the tiny neutrino mass. By analyzing the energy of the electrons emitted in this decay, CATRIN aims to set an upper limit on the neutrino mass, pushing the boundaries of discernibility. CATRIN has already made significant progress, setting an upper limit on the neutrino mass of 0.8 electron volts with sensitivity down to 0.2 electron volts. However, this may not be sufficient to determine the true neutrino mass, which may be even smaller. This realization has sparked a global effort to develop alternative methods and experiments that could surpass the capabilities of CATRIN. Among these alternative approaches is the use of holmium-163 in electron capture experiments. Unlike tritium, holmium-163 decays via electron capture when an electron is absorbed by the nucleus, resulting in the emission of a neutrino and a photon. This releases a minuscule amount of heat that can be detected by extremely sensitive equipment. Experiments with holmium-163 have already demonstrated highly accurate energy measurements, and physicists aim to increase their sensitivity by an order of magnitude. Another promising direction is the Project 8 experiment, which uses a magnetic bottle to capture electrons from beta decay in gaseous tritium. By analyzing the radio waves emitted by these captured electrons, researchers can obtain precise measurements of their energies. Project 8 aims to achieve a sensitivity of up to 0.04 eV, which could surpass the limit set by cosmological studies and provide crucial data on the true mass of neutrinos. The quest to understand neutrinos is not confined to one country or continent. It's truly a global endeavor. The challenges posed by these elusive particles have brought together scientists from around the world, fostering collaboration across borders. As we await the first signals from Japan's Hyper-K, which is already taking shape in a newly dug cave, and await news from Dune, nestled deep in an old South Dakota gold mine, the next chapter in our understanding of the universe is just beginning. Stay tuned as we journey through the frontiers of science, making one discovery at a time. You've probably heard of dark matter, the elusive substance that makes up about 1/4 of the universe. That ghostly puppeteer is pulling the strings of the galaxy but never showing itself. But what if dark matter is just the tip of the cosmic iceberg? Imagine a universe where the scales of gravity tip in mysterious ways, where stars and binary systems, two stars orbiting a common center, defy the very laws established by Newton and Einstein. What if their equations are not the final word? Recent research suggests anomalies and deviations in the orbital dance of double stars that neither dark matter nor our current understanding of gravity can fully explain. So, are we on the cusp of a paradigm shift? Is our view of the cosmos not as stable as we thought? In cosmic ballet, stars are the prima donnas that catch our eye. But have you ever wondered how these celestial luminaries come into being? It all starts in the dark, cold corners of a nebula, a vast cloud of gas and dust. Gravity plays a key role here, pulling the particles closer and closer until they no longer resist gravity. They merge, triggering a nuclear fusion reaction that produces a star. However, the life of a star does not last forever. There comes a point when the nuclear fuel runs out, and the star faces its inevitable demise. For massive stars, this end is nothing short of spectacular. A supernova explosion that eclipses entire galaxies, if only for a short time. These supernovae are not just cosmic fireworks. They are the forges of the universe. It's in the crucible of these explosions that elements heavier than iron are created. So the gold in your jewelry, the calcium in your bones, it's all stardust. The remnants of a supernova explosion. But here's where the plot gets twisted. In a universe dominated by dark matter, these stars and their explosive deaths are part of a larger scene. Dark matter, with its gravitational pull, influences the formation of galaxies and the distribution of stars within them. Imagine two galaxies, one with dark matter and one without. In the galaxy with dark matter, the gravitational forces are so strong that they can cause bursts of star formation, leading to a higher number of supernovae. In these galaxies, stars form and die at an accelerated rate, creating a dynamic and ever-changing landscape. Recent studies have even quantified this relationship, showing a direct correlation between the amount of dark matter in a galaxy and the rate of star formation. But what if this correlation is not as simple as it seems? Enter MOND, Modified Newtonian Dynamics. This theory suggests that gravity behaves differently at very small accelerations. If MOND is correct, the high rate of star formation in dark matter-rich galaxies may have an alternative explanation. Double star systems, those cosmic pairs we discussed earlier, can serve as an ideal test laboratory for these theories. Their orbital dynamics can show whether Newtonian gravity persists or whether MOND offers a better explanation. As scientists delve deeper into the data, especially the treasure trove provided by the Gaia mission, we're getting closer to understanding the true nature of this galactic dance. In cosmic narratives, dark matter is often portrayed as a silent, mysterious entity that shapes galaxies but remains elusive. One of the most compelling theories attempting to solve this mystery is the cold dark matter model, or CDM. In the CDM model, dark matter is cold, which means that its particles move much slower than the speed of light. This slowness allows them to clump together to form the gravitational scaffolding on which galaxies are built. CDM-based computer modeling has been extremely successful in reconstructing the large-scale structure of the universe. It shows a cosmic network of galaxies connected by dark matter filaments that's very similar to what we observe. But, like any good story, there are unexpected plot twists. While CDM does an excellent job of explaining the grand architecture of the universe, it falters when we get closer to individual galaxies. Take, for example, the rotation curves of galaxies, the speed at which stars and gas rotate around the galactic center. According to Newtonian physics and the CDM model, this speed should drop sharply as we move away from the center. But observations tell a different story. The rotation curves remain surprisingly flat, suggesting that something else is involved here. Perhaps another kind of dark matter, or even a modification of gravity. And then there are dwarf galaxies, smaller satellites of larger galaxies like our Milky Way. The CDM model predicts many of these dwarf galaxies, but we just don't see as many as expected. These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing an important piece of the cosmic puzzle? This is where MOND enters the scene again, offering a different set of equations that better explain these galactic features. It's like two different scripts of the same movie, each with its interpretation of the main character, dark matter. At check weighing, the scientific community is divided. Is the CDM the final theory that unifies our understanding of the universe, or is it just a stepping stone toward a more complete model? For centuries, Sir Isaac Newton's equations have been the foundation of our understanding of gravity. They've been tested, retested, and retested, and have stood the test of time. But what if there is more to the story? Introducing MOND, or Modified Newtonian Dynamics, a theory that dares to modify Newton's sacred equations. It suggests that gravity behaves differently at extremely low accelerations, such as at the outskirts of galaxies. The goal of MOND, conceived by physicist Mordecai Milgram in the early 1980s, is to resolve some of the inconsistencies that have arisen in our observations of galaxies, especially those puzzling rotation curves we discussed earlier. You see, MOND fits the observed flat rotation curves of galaxies perfectly, without resorting to dark matter. It's as if MOND is saying, wait, maybe you don't need to invent a mysterious form of matter. Maybe you just need to adjust your equations. And it's not just about rotation curves. MOND has also managed to explain the dynamics of some galaxy clusters, and even the large-scale structure of the universe, without relying on the mysterious dark matter. But of course, no theory is without problems. While MOND succeeds in some areas, it faces difficulties in others. Explaining the cosmic microwave background afterglow of the Big Bang. The cosmic microwave background, or CMB, is a snapshot of the universe just 380,000 years after the Big Bang. The CDM model, with its dark matter component, explains the features of the relic radiation well. MOND, however, has difficulties here. And let's not forget our celestial pairs, double star systems. Recent studies, some of which we've already discussed, have shown contradictory results when applying MOND to double stars. So what does that give us? Well, at the very least, a state of exciting uncertainty. As new data comes in, especially from the Gaia mission, MOND continues to be hotly debated. Is MOND the missing piece of the puzzle that will finally explain the anomalies we observe? Or is it a useful but ultimately flawed stepping stone towards a more complete theory? In a universe full of questions, sometimes the answers lie closer to home. Just 1.5 million kilometers from Earth orbits Gaia, a spacecraft that may hold the keys to some of the universe's most puzzling mysteries. Launched by the European Space Agency in 2013, Gaia is no ordinary telescope. It's a space cartographer mapping the positions, distances, and motions of more than 1 billion stars with unprecedented accuracy. Imagine having the coordinates of 1 billion stars at your fingertips. It's like Google Maps for the Milky Way, but with a staggering level of detail. One of Gaia's key techniques is parallax, an ancient method with a modern interpretation. By observing a star from 2 different points in its orbit, Gaia can triangulate the distance to the star with incredible accuracy. But Gaia is more than just a space explorer, it's a theory tester. Remember those controversial theories about gravity and dark matter? Gaia data can be used to put those theories under the microscope. Take, for example, double star systems. These systems are crucial for testing theories like MOND. Gaia's precise measurements of the positions and velocities of these stars can help us understand which theory is correct. And it's not just stars. Gaia also observes asteroids, planets, and even distant galaxies. Its data have been used to refine the Hubble constant, a key parameter that helps us understand the expansion rate of the universe. Measuring the Hubble constant with Gaia has added a new twist to the ongoing cosmic controversy. Different methods yielded slightly different values, and Gaia's data became an important piece of this cosmic puzzle. But the Gaia mission is not without its challenges. While the spacecraft provides a wealth of data, interpreting that data is a different story. The same Gaia data have been used to both support and refute theories such as CDM and MOND, leading to heated debates in the scientific community. It's like a high-resolution photograph where everyone sees something different. Is it a speck on the lens or a revolutionary discovery? Interpretation depends on sophisticated statistical methods and, of course, on our basic assumptions about the universe. There is nothing more fascinating than double stars. 2 stars locked in a gravitational embrace, orbiting each other in a delicate balance of attraction and repulsion. As we mentioned earlier, these dual systems are not just celestial spectacles, they are cosmic laboratories. Here, in the intricate ballet of their orbits, we can test our deepest theories about the nature of gravity itself. Double stars have been a cornerstone of astronomical research for centuries. They've helped us measure the mass of stars, understand stellar evolution, and even confirm Einstein's general theory of relativity. But in the context of our ongoing debate between cold, dark matter and modified Newtonian dynamics, double stars play an even more important role. Their orbital dynamics can reveal whether Newtonian gravity persists or whether MOND offers a better explanation. Recent studies have delved deeper into this question. Some studies, using data from the Gaia mission, have shown that double star systems behave as predicted by Newtonian gravity, casting doubt on the applicability of MOND. However, other studies tell a different story. They suggest that MOND is better suited for some double systems. especially those with large distances between them and weak gravitational attraction. Could it be that both theories are partially correct? Or are we missing a key piece of the puzzle? The scientific community is divided, and for good reason. The stakes are high. The behavior of double stars could either confirm our current theories or send us back to the drawing board in our quest to understand the universe. So, how do we weigh evidence? Meet Bayesian statistics, a mathematical framework that might just tip the scales. Named after Thomas Bayes, an 18th century statistician and theologian, Bayesian statistics offers a way to update our beliefs in light of new data. It's like a mathematical expression of the scientific method itself. Here's how it works. You start with a prior belief, or prior, which is your initial hypothesis. As new data becomes available, you update it before forming a posterior hypothesis, a revised hypothesis that better fits the actual data. In the context of our cosmic debate, be it cold dark matter, MOND, or something completely different, Bayesian statistics provides a rigorous way to assess which theory is more likely, given the observed data. For example, when analyzing double star systems, Bayesian methods can help quantify the probability that MOND, or Newtonian gravity, is the correct theory. It's not just about curve fitting, it's about estimating the weight of evidence. And it doesn't just apply to double stars. Bayesian statistics have been applied to a wide range of cosmic phenomena, from the distribution of dark matter in galaxy clusters to the rate of expansion of the universe. Nevertheless, Bayesian methods are not without critics. One of the most controversial points is the choice of a prior. How to choose the initial hypothesis in a way that does not distort the result. The choice of a prior can be controversial because it can affect the results. If your prior leans strongly towards one theory, a posterior may confirm that theory even if the other is equally true. As we grapple with these questions, Bayesian statistics remain a powerful tool in our analytical arsenal. It offers a way to make sense of complex spatial data, sift through the noise, and find the signal. The universe seems to refuse to reveal its secrets readily. Even as we gather more data, the debate about the true nature of gravity is intensifying. Hyun Che, an astronomer who recently hit the headlines, said, quote, "I was feeling like I was dreaming. It seemed so unreal. This is because my results did not match any previous results." Che's work stirred the pot by suggesting that when the gravitational acceleration of stars in certain double systems falls below a certain threshold, they're more consistent with MOND models than with the standard gravity model. But here's the rub. Che's findings contradict several previous studies. He mentions, quote, "One group has been claiming an anomaly for some time, but the anomaly seemed not to match well the predictions of existing modified gravity theories." This discrepancy in results is not just a glitch. It's a fundamental challenge to our understanding of the cosmos. It raises questions about the reliability of our models and the data we use to test them. So what does that give us? Well, at least a state of productive confusion. As Che concludes, quote, "Because the standard cosmology is based on general relativity, cosmology needs a major revision now." The debate is far from over. As we collect more data and refine our theories, the search for the ultimate truth about gravity and the universe continues. And in this quest, every anomaly, every contradictory result adds a new level of complexity and wonder. In the infinite depths of the universe lies a fundamental principle, as mysterious as it is omnipresent. This force governs the very fabric of existence, yet remains elusive to the casual observer. This is the story of entropy, a concept that reveals the hidden order in the apparent chaos of the cosmos. Here on Earth, entropy is evident in every rustling leaf, every rolling wave, and every moving cloud. It's the quiet organizer of natural processes, from the simplest to the most complex. But what is entropy really? It's a phenomenon often misunderstood as an ordinary disorder, but it's more than that. Entropy is a transformation, a movement from order to disorder, from concentration to dissipation. This is exactly why your coffee gets cold, why the ice melts, why the scent of flowers dissipates in the air. So let us understand how an order is hidden in what appears to be chaos, and how does this mysterious force shape our entire environment, from the smallest particle to the largest galaxy, and even the very course of life itself. There is a hidden force at work in every corner of our world, from the quiet forests to the bustling hearts of our cities. This force, often unnoticed, plays a key role in the great work of the universe. Imagine a dewdrop on a leaf, shimmering in the morning sunlight. As the sun rises, the dewdrop slowly disappears, and its particles disperse into the air. This phenomenon illustrates a fundamental principle of nature, the transition from a concentrated state, the dewdrop, to a dispersed state, the water vapor in the air. At the molecular level, this principle manifests itself as the tendency of particles to move from a state of concentration to a state of dispersion. This is similar to the way a crowd disperses after a concert, moving from a structured gathering to random scattered groups. In the center of our cities, this principle is reflected in the rhythm of daily life. The concentrated bustle of the morning rush hour gradually fades away as the day progresses. Entropy is often misunderstood as simple chaos or disorder, but it's much more nuanced than that. It's about transformation and change. Like a sandcastle slowly crumbling under the merciless waves, entropy is the inevitable transition from order to disorder. This concept is encapsulated in the second law of thermodynamics, a fundamental principle of physics. It states that in any closed system, entropy will either remain constant or increase over time. In other words, the natural course of the universe is toward greater dispersion and disorder. From the grand scale of the cosmos, where stars and galaxies form and disappear, to the minutiae of our daily lives. This principle is a universal constant. It governs the birth and death of stars, the flow of rivers, and even the fading heat in a coffee cup. Imagine a steaming cup of coffee left on a table. Over time, its heat dissipates into the surrounding air, cooling the coffee. This is entropy in action, redistributing energy from a concentrated state, hot coffee, to a more diffuse state, a cold room. Or take an ice cube, melting on a warm day. The structured, solid form of ice turns into a puddle of water, whose molecules are free to move. This transition from a solid, ordered state to a fluid, disordered state is a classic example of increasing entropy. In every aspect of our universe, this quiet but relentless force is always present, subtly directing the flow of energy and matter. As we delve deeper into the theory, it's crucial to go back in time to the era when the concept first emerged. The history of entropy is intertwined with the minds of some of the most brilliant scientists in history. Our narrative begins with Sadi Carnot, a French physicist often referred to as the father of thermodynamics. In the early 19th century, Carnot was fascinated by the efficiency of steam engines, the driving force behind the Industrial Revolution. His research laid the foundation for the laws of thermodynamics, which were later incorporated into the concept of entropy. Carnot's visionary work described how heat engines work and focused on how energy is transferred and transformed. His theories have played a crucial role in understanding the dynamics of energy flow within systems. The next key figure in our story is Rudolf Clausius, a German physicist. Clausius was the one who introduced the term entropy in the mid-19th century. He built on Carnot's ideas by delving into the nature of heat and energy transfer. Clausius's work led to a more formal definition of entropy. He suggested that heat cannot spontaneously transfer from a colder body to a hotter one, the principle underlying the second law of thermodynamics. His mathematical formulation of this concept allowed it to be quantified, bringing clarity to its elusive nature. Another giant in this field was Ludwig Boltzmann, an Austrian physicist. Boltzmann's contributions in the late 19th century brought a statistical approach to thermodynamics. He linked the microscopic behavior of atoms and molecules to macroscopic properties of matter, such as temperature and entropy. Boltzmann's work was groundbreaking. He showed that entropy can be understood as a measure of disorder at the molecular level. His famous formula, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of microstates, gave a profound insight into the nature of this phenomenon. The legacy of these pioneering scientists is immense. Their collective work laid the foundation for modern thermodynamics and statistical mechanics, fields that continue to evolve and shape our understanding of the universe. Turning our gaze to the natural world, we find that entropy is at work in every ecosystem, shaping the environment and the life within it. Nature, in its infinite complexity, is a vivid canvas of disorder in action. Consider a fallen tree in the forest. Over time, it undergoes a remarkable transformation. Microorganisms, insects, and fungi break it down, returning nutrients to the soil. This process of decay and renewal is a manifestation of our principle, reflecting the cycle of life and death in nature. Rivers are also agents of entropy. They constantly change the landscape, cutting through rock and soil, and redistributing sediments from the mountains to the sea. This relentless movement and transformation of matter is a classic example of the role of this principle in geophysical processes. Weather is another area in which chaos plays a crucial role. Cloud formation, rainfall, snowmelt. These are all processes driven by the distribution and redistribution of energy in the atmosphere on a global scale. In the oceans, entropy is manifested in the life cycles of marine ecosystems. Coral reefs, for example, thrive on the delicate balance of nutrient cycles, temperature, and ocean currents governed by the principles of energy flow. Photosynthesis, the process by which plants convert sunlight into energy, is another interesting example. Here, the entropy principle plays a role in converting solar energy into chemical energy, a process fundamental to life on Earth. From the tiniest interactions of microscopic organisms to the grandeur of ecological systems, this fundamental force is the invisible conductor of the natural world. It is the underlying principle that nurtures the beauty and dynamism of our planet. Life on Earth, in all its diverse forms, is deeply intertwined with the principles of energy flow and transformation. This complex relationship between life and energy reveals a universe in which chaos and order coexist in a delicate balance. Consider the simple process of seed germination. This process is a microcosm of life's ability to use and organize energy. As the seed grows, it absorbs energy from the environment, converting it into structured, organized forms. However, there's a price to pay for this organization, an increase in the overall disorderliness of the system. In the human body, entropy is our constant companion. Our cells are energy conversion power plants, constantly converting nutrients into energy. This metabolic activity is vital to our existence, but it also leads to increased disorder as energy is released in the form of heat and waste products. Ecosystems are also valid examples. For example, in a rainforest, the flow of energy from the sun to plants and then through the food chain demonstrates the role of entropy in ecological processes. Each transfer of energy from one organism to another involves energy dissipation, contributing to the overall disorder of the ecosystem. Looking at the bigger picture, the evolution of life on Earth can be seen as a journey through entropy, from the first single-celled organisms to the complex network of life we see today. Evolution has been a process of increasing complexity, driven by the fundamental laws of energy and matter. In the grand narrative of life, entropy is not just a concept of decay or disorder. It's the driving force behind growth, complexity, and a constant cycle of transformation. Life in all its forms thrives in the delicate balance between order and chaos, a testament to the profound interplay of energy and matter. In the cosmic arena, the principles governing entropy show a universe in constant motion, a stage in which stars are born, live, and die in a great cycle of energy transformation. Star formation is a process of remarkable energy dynamics. Inside nebula, clouds of gas and dust collapse under gravity, heating up and eventually triggering nuclear fusion. It's a transition from potential energy to kinetic energy, a cosmic example of energy distribution on an enormous scale. The life cycle of stars can be seen as a narrative of energy transformation. In their final moments, massive stars explode as supernovae, dispersing their elements across the cosmos. This dispersion is a powerful demonstration of the universe's tendency to increase the dispersion of energy and matter. Black holes, in turn, represent one of the most intriguing aspects of cosmic entropy. These mysterious objects, which have such a strong gravitational pull that even light cannot escape them, play a significant role in the energy dynamics of the universe. The black hole event horizon marks the point of no return, where matter and energy are irreversibly absorbed, contributing to the overall disorder of the cosmos. By the way, our channel has already published a detailed video about the connection between black holes, Hawking radiation that depletes them, and entropy. We recommend you watch it. The expansion of the universe is itself a confirmation of these principles. Galaxies are diverging, energy is becoming more evenly distributed over vast space, and the fabric of the cosmos is stretching, all of which indicate that the universe is evolving toward a state of higher dispersion. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a glimpse into the early universe. As we know, this radiation is a remnant of a time when the universe was hot, dense, and in a lower entropy state. Paradoxically, as the universe expanded and cooled, its randomness increased. And this is what led to the inevitable formation of the complex structures we see today. One of the most profound consequences of these cosmic processes is the concept of the heat death of the universe. In this scenario, the universe reaches a state of maximum entropy, where all energy is distributed so uniformly that further energy transformations become impossible. This is a future in which the universe is cold, dark, and devoid of the energetic dynamics that drive cosmic evolution. In this vast cosmic action, the flow and transformation of energy shapes not only the stars and galaxies, but also the very destiny of the universe. It is a continuous process of creation, transformation, and ultimately, disintegration. In the modern world, the concept of entropy has transcended its scientific origins, finding applications in a variety of fields, but subject to common misconceptions. Currently, entropy plays a crucial role in the development of advanced technologies. In the field of renewable energy, a thorough understanding of this concept is essential to improve the efficiency of solar panels, wind turbines, and energy storage systems. This knowledge greatly helps in optimizing the conversion of natural energy sources into usable energy. In the field of information theory, entropy has acquired a new meaning. It represents a measure of uncertainty or randomness in a system. This concept is crucial in data encryption and compression, where controlling and predicting information patterns is essential. Despite its scientific importance, entropy is often misinterpreted. A common misconception is to equate entropy solely with disorder or chaos. Meanwhile, while the definition that entropy leads to an increase in disorder is correct, it is worth clarifying that we're talking about the distribution of energy and the probability of certain states. Another misconception is the notion that entropy can be reversed or overcome. In popular culture, we see images of time reversal or spontaneous assembly of objects. However, according to the second law of thermodynamics, in a closed system, entropy can only increase or remain constant. Modern physics research is considering its impact on quantum mechanics, the behavior of black holes, and the ultimate fate of the universe. Beyond theoretical physics, entropy has practical applications in environmental science, engineering, and urban planning. It helps to model climate change, design sustainable systems, and understand urban development patterns. The future will undoubtedly bring new challenges and opportunities, and our understanding of this phenomenon will be critical in addressing them. Whether it is advancing technology, exploring space, or managing our planet and conserving its resources, entropy remains a fundamental concept that will continue to define our journey into the unknown. Imagine a canvas of moments woven with the threads of time. Matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomenon. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch. and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between two distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes, mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier, known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort spacetime enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explore the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time? For years now, there's been a concept that defies the very laws of physics as we know them, a dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction, it's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine, science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of spacetime. Alcubierre hypothesized that if we could manipulate spacetime in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of spacetime. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter, remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects, or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem: the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they They also raise questions about the feasibility of long-duration travel using Alcubierre drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery. Have you ever heard of a galaxy that defies categorization? Imagine a cosmic structure that combines an ancient dormant core surrounded by a bright halo of young stars. This is not your typical spiral or elliptical galaxy, but something much more mysterious. A Hogue object. Initially mistaken for a planetary nebula or gravitational lens, the true nature of Hogue's object remained hidden until more advanced observations revealed its unique structure. The central elliptical core appears red and inactive, while the outer ring is bright blue, teeming with new star formation. A clear gap separates the two components as if they belong to different galaxies. The object spans an impressive 121,000 light-years wide, with a central core about 17,000 light-years across and an outer ring stretching out 75,000 light-years. This apparent gap between the core and the ring is wider than the ring itself, which is a surprising feature for such a colossal galaxy. Ring galaxies, like Hogue's object, are extremely rare, making up less than 0.1% of all known galaxies. They often arise from complex cosmic events, but Hogue's object seems to maintain a calm and orderly appearance, which further deepens the mystery. Despite decades of research, astronomers are still grappling with the question of the origin of this galaxy. Was it the result of a quiet accretion process, or did a cosmic collision play a role? Arthur Hogue, a prominent astronomer of the mid-20th century, made a discovery that would intrigue and puzzle scientists for decades to come. In 1950, while conducting a study of the night sky, the astronomer came across a celestial object that defied conventional classification. This object, later named after him, had characteristics unlike any previously observed galaxy. At first glance, Hogue's object appeared to be a planetary nebula, a cloud of gas and dust surrounding a dying star. However, its unusual structure, consisting of a central core surrounded by a luminous ring, suggested otherwise. Early images taken by the astronomer's telescope showed a clear separation between the inner and outer components, prompting curiosity and speculation. Initial hypotheses varied widely. Hogue himself hypothesized that it could be a planetary nebula, or even a gravitational lens. The gravitational lens hypothesis suggested that the object was not a galaxy at all, but rather a massive elliptical galaxy magnifying a background galaxy in a ring-like shape. Gravitational lenses occur when a massive object, such as an elliptical galaxy, bends the light of a more distant object behind it. This bending creates a ring of light around the foreground object, known as the Einstein ring. In early observations, the outer ring of Hogue's object resembled such a lens, suggesting that it may be a foreground galaxy amplifying the light of a more distant object. For nearly 4 decades, the true nature of the Hogue object remained uncertain. It was not until 1987 that astronomers equipped with better technology were able to confirm the connection between the ring and the nucleus through spectroscopic analysis of the red shift. This shift is due to the expansion of the universe, with more distant objects exhibiting a greater redshift. By analyzing the redshift of the core and ring of Hogue's object, astronomers confirmed that they're not separate entities, but components of the same galaxy. This discovery debunked the gravitational lens hypothesis and cemented the status of the Hogue object as a unique type of galaxy. The central core, consisting of old red stars, contrasts sharply with the outer ring, which is bright blue and actively forming new stars. It is this special composition and structure that distinguishes Hoag's object from typical spiral and elliptical galaxies. Ring galaxies are rare, making up less than 0.1% of all known galaxies. Typical spiral galaxies have sprawling arms of stars, while elliptical galaxies have a more uniform, rounded shape. The Hoag object, with its perfectly separated nucleus and ring, remains one of the most well-defined examples of this rare class of galaxies. The discovery began the scientific journey to understand one of the most mysterious structures in the universe. Today, with the help of modern telescopes and ongoing research, astronomers are trying to unravel the mysteries surrounding this fascinating cosmic anomaly. Its quiet appearance, distinct breakup, and combination of an ancient core with a young, star-forming ring make Object Hoag a unique and enigmatic galaxy, prompting astronomers to investigate various theories of its origin and evolution. Thus, one of the main theories proposed to explain the formation of the Hoag object is the collision hypothesis. According to this theory, the characteristic ring structure of the galaxy arose as a result of a high-speed collision of a smaller galaxy with a larger one. When a smaller galaxy collides with a larger galaxy, the impact generates a density wave that rushes outward from the center of the larger galaxy. This wave compresses the interstellar gas, causing star formation in the ring around the galaxy's nucleus. The Cartwheel galaxy, with its strikingly similar ring structure, is a classic example of this process. In the case of a Hoag object, if a smaller galaxy collided with it, we would expect to detect several key features. First, the collision would create density waves that push the gas and stars outward, forming a ring. Moreover, the stars in the ring should have exhibited high relative velocities, indicating the kinetic energy from the collision. And third, in or near the ring, there would be residual fragments or remnants of colliding galaxies. However, detailed observations of Hoag's object have revealed some inconsistencies with the collision hypothesis. The ring stars do not exhibit the high relative velocities that are usually associated with such events. In addition, there's a notable absence of residual fragments or evidence of a second galaxy. To test this hypothesis, models of galaxy collisions have been used. These models show that although a collision may produce a ring structure, the resulting galaxy often retains traces of violent interaction. The Hoag object, which has a calm and symmetrical appearance, lacks these chaotic features, suggesting a more complex formation history. However, another intriguing possibility looms on the horizon: resonance theory. Could a galaxy's ring structure be the result of gravitational interactions within a spiral galaxy? Let's explore this question. Another fascinating theory explaining the formation of the Hoag object is the resonance theory. According to this theory, the ring structure of a galaxy can arise as a result of the internal dynamics of barred spiral galaxies, in particular due to resonance in the gravitational field. Spiral galaxies are characterized by the structure of a central bar, from the ends of which spiral arms branch off. These bars play a crucial role in the dynamics and evolution of the galaxy. According to theory, as the bar rotates, it can create a resonance that affects the distribution of gas and stars within the galaxy. Resonance occurs when gravitational forces within a galaxy create regions in which the rotational velocities of stars and gas clouds synchronize. These regions can trap gas and stars, resulting in the formation of rings. There are several basic types of resonances. Inner Lindblad resonance occurs near a galaxy center, often forming an inner ring. Outer Lindblad resonance arising further, potentially forming an outer ring. The third type is co-rotation resonance, a region where the rotational velocity of the bar coincides with the orbital velocity of the stars and gas, which can also lead to ring formation. In the case of the Hoag object, the presence of a ring around the elliptical core suggests that such resonances may have played a role in its formation. The bar structure could have caused a resonance that trapped gas and stars at certain radii, creating the distinct ring we see today. When the bar rotates, it exerts a gravitational influence that can reorganize the gas and stars of the galaxy. Over time, this process can lead to the formation of a well-defined ring structure. Resonance theory provides a mechanism for how a spiral galaxy can evolve into a ring galaxy without a collision. NGC 1291 is a classic example of a galaxy in which resonance effects likely played a role in ring formation. The central band and outer ring provide a visual analogy of what may have happened in Hoag's object. However, the resonance theory faces difficulties when applied to the Hoag object. In particular, the Hoag object currently has no central bar. This absence raises the question of whether the bar may have existed in the past and subsequently dissipated, or whether other processes may have contributed to the formation of the ring. However, there is another interesting and equally plausible theory: the accretion theory. Can the gradual accumulation of intergalactic gas explain the unique structure of the galaxy? Let's explore this in more detail. The third major theory proposed to explain the formation of the Hoag object is the accretion theory. According to this theory, the unique structure of the galaxy resulted from the gradual accumulation of intergalactic gas, rather than from a dramatic collision or internal resonance. Accretion is the process by which a galaxy collects gas from the surrounding intergalactic medium over a long period of time. This gas is entrained by gravitational attraction, gradually accumulating and forming new structures. In the case of the Hoag object, it's likely that a central elliptical core formed first. Over time, the gravity of this core attracted gas from the intergalactic medium. As the gas approached the nucleus, it began to rotate around it, forming a ring structure due to angular momentum conservation. As gas accumulated in the ring, its density reached a high enough density to trigger star formation. This process explains the bright blue color of the ring, indicating active, ongoing star formation. And the gap between the core and the ring is explained by the balance of gravitational forces and the dynamics of the infalling gas. Galaxies such as NGC 6028 provide an example of how accretion can lead to the formation of ring structures. These galaxies show similar features: older central nuclei and younger rings of star-forming regions, which supports accretion theory as a plausible explanation. While the accretion theory provides a plausible explanation, it also raises questions. Why does the ring form at a particular radius? How did the dynamics of gas influx and star formation balance create such a clear separation between the core and the ring? These questions continue to drive research and exploration. Continued observations have provided evidence to support this theory. The ring of Hoag's object contains more gas mass than the entire Milky Way, suggesting significant accretion of intergalactic material. In addition, the well-defined structure of the ring and the absence of chaotic remnants are consistent with a gradual and orderly accretion process. Recent research has also significantly deepened this theory. By modeling the gravitational interaction in such ring systems, scientists have shown how the balance of forces can create stable and unstable orbits, leading to discontinuities in the distribution of matter. These results are consistent with the observed structure of the Hoag object, where the gap between the core and the ring is a region of unstable circular orbits, further supporting the theory. Also, the accretion theory offers a quite convincing explanation for the formation, suggesting that the galaxy grew and evolved through the slow accumulation of surrounding gas. This process contrasts with the more violent and destructive events described in the collision and resonance theories. However, each of these proposed theories, collision, resonance, and accretion, has their own flaws, leaving several unanswered questions. Although the collision hypothesis explains the formation of the ring by density waves created by galaxy collisions, it does not explain the ordered structure of the object and the absence of residual fragments and high relative velocities commonly observed in such events. Resonance theory, on the other hand, suggests that internal gravitational resonances within a twisted spiral galaxy can create ring structures. However, it's clear that Hoag's object lacks the central bar necessary for this process, and the theory does not fully explain the apparent gap between the nucleus and the ring. Accretion theory, in turn, argues that the gradual accumulation of intergalactic gas forms a ring. While this explains the ordered structure and ongoing star formation, questions arise as to why the ring forms at a particular radius, and how the dynamics between the core and the ring create such a distinct gap. Despite these theories, several mysteries remain. Why is there a significant gap between the nucleus and the ring? What specific conditions led to the formation of such a well-defined structure? And how do gravitational forces and dynamics within the galaxy interact to maintain this balance? Future telescope missions, such as the Nancy Grace Roman Space Telescope and the soon-to-be-launched Extremely Large Telescope, are designed to provide a deeper understanding of such questions. These advanced observatories will provide higher resolution images and more detailed spectroscopic data, potentially revealing the processes underlying the formation of such ring galaxies. As we explore the cosmos, Hoag's object remains a testament to the diverse and complex processes that form galaxies, and remind us once again that there are still mysteries in the cosmos waiting to be discovered. Our universe hides a mystery that's long captivated the human mind. A question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded, where the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And maybe we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? This standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems, phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, phase space expands, branching out into almost infinite possibilities. Each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply the product of chance, or is there a deeper cause? Let us consider two sharply contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. So, central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler, measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins to a variety of forms combined into the complex ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see the complexity of life as not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now turn to a very trivial question, but one that shines in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher assembly index, the more likely it is that these molecules are the result of life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know. Life on Earth. What if it doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those that are very different from terrestrial environments. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. So assembly theory offers a new way of looking at life, not just as a biological phenomenon, but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here, in this chaotic environment, simple molecules began the journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper. Life, according to assembly theory, emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain structure. In other words, we can say this is the blueprint for life. In the world of assembly theory, this is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, is what drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads, being questioned by critical voices such as Dr. Hector Zennel. The critique presented by Zennel raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article will require time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counter-arguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges? Or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have initiated a conversation about the nature of scientific discovery. They emphasized the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, such theories will come and go. but the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of the interest of scientific research. In a universe dominated by ancient massive structures, there are places where something unexpected happens that defies the cosmic norm. New galaxies emerge. These rare formations are changing our idea of how the cosmos should behave. While the Milky Way and Andromeda seem to have entered their mature phase, somewhere out there in the far corners of space, young galaxies are still being born, glowing with the energy of new star formation. But why do these exceptions exist? What forces allow them to thrive when the rest of the universe has slowed down? By exploring these distant regions, we learn about the forces that lead to the formation of such grand structures, the role of dark matter in all of this, and the mysterious processes that allow some galaxies to defy the passage of time. The discovery and classification of galaxies was a milestone in our understanding of the universe. In the early 20th century, observations by Edwin Hubble showed that the nebulae observed in telescopes were not just gas clouds inside our galaxy, but entire galaxies, each containing billions of stars. This discovery expanded our understanding of the cosmos beyond the Milky Way, revealing a universe teeming with distant galaxies. Soon galaxies were categorized by their shape: spiral, elliptical, and irregular. These classifications helped astronomers create a more organized view of the cosmos, which led to further study of the origin and evolution of these huge structures. However, as our observations deepened, a surprising pattern emerged. The vast majority of galaxies observed were ancient, dating back almost to the very beginning of the universe. This discovery was unexpected. When the first detailed studies of galaxies were conducted, scientists expected to find a range of galaxy ages, including recently formed galaxies. However, instead of a universe full of young galaxies still in the formation stage, they found that most galaxies had already reached maturity. These findings challenged existing theories of cosmic evolution at the time, raising questions about how and when galaxies formed. At first, the scientific community was stunned. The rarity of young galaxies seemed to contradict the ongoing process of star formation that's still observed in the universe today. This paradox, the presence of ongoing star formation in predominantly ancient galaxies, posed a serious question to our understanding of galaxy formation and evolution. As astronomers delved deeper into this mystery, they began to realize that the formation of galaxies may not be as simple as previously thought. The processes that govern the early universe, such as the distribution of dark matter and the influence of cosmic structures, seem to have played a more important role in shaping its landscape than first thought. These factors likely contributed to the rapid formation of galaxies shortly after the Big Bang, leading to a shortage of newly formed ones in the modern era. Determining the age of galaxies is a complex task that relies on a variety of methods, most of which focus on the age of the stars within them. For example, astronomers have used several methods to estimate the age of the stellar population of the Milky Way and Andromeda. One of the main methods involves studying the distribution of stars in the Hertzsprung-Russell diagram, or HR diagram, which shows the dependence of the luminosity of stars on their temperature. In particular, astronomers focus on the turning point of the main sequence, the stage at which stars begin to leave the main sequence and turn into red giants. This point is very sensitive to age. The position of the pivot point on the HR diagram can give an accurate estimate of the age of the stellar population. Another important method is the study of globular clusters, dense groups of ancient stars orbiting around the outskirts of galaxies. The age of these clusters is also determined by the rotation points of the main sequence of their stars. And since globular clusters are among the oldest objects in the galaxy, they provide crucial clues about their formation history. For example, the oldest globular clusters in the Milky Way are about 13 billion years old, indicating that the Milky Way itself formed shortly after the Big Bang. In addition to studying star clusters, astronomers also use spectral analysis. By analyzing light spectra, particularly absorption lines, they can determine the relative proportions of different types of stars. Older galaxies are dominated by red, cooler stars, while younger galaxies have more blue, hotter stars. The discovery that many galaxies, including the Milky Way, formed nearly 13.8 billion years ago, shortly after the Big Bang, was a significant breakthrough in cosmology. The rapid collapse of clouds of primordial gas under the influence of dark matter probably played a crucial role in these early formations. This process laid the foundation for the cosmic structures we see today. So the formation of galaxies in the early universe is a story deeply intertwined with the mysterious and influential presence of dark matter. In the chaotic period after the Big Bang, the universe was a hot, dense soup of particles in which matter and radiation were tightly bound together. As the universe expanded and cooled, gravity began to pull matter together into the first structures, tiny clumps of matter known as proto-galaxies. According to scientists, dark matter played a key role in this process. Unlike ordinary matter, which interacts through the electromagnetic forces and radiation, dark matter interacts mainly through gravity. Because of this, dark matter began to stick together earlier than ordinary matter, forming the basis on which the first galaxies eventually formed. These dense regions of dark matter, often called dark matter halos, provided the gravitational wells needed to pull in gas and dust, leading to the formation of the first stars and eventually the first galaxies. These early galaxies were relatively small and simple compared to the huge and complex galaxies we see today. They were often irregularly shaped and lacking a distinct structure, such as that of the Milky Way. But over time, driven by the gravitational pull of dark matter, these proto-galaxies began to merge and interact. As proto-galaxies merged, they grew in size and complexity, forming more massive structures that eventually evolved into the spirals, ellipticals, and irregular shapes that populate the modern universe. This period of intense formation and merger is often referred to as cosmic noon, a time of active star formation and growth through mergers at a much higher rate than we observe in the modern universe. So why are newly formed galaxies such a rarity in the modern universe? One of the key factors contributing to this phenomenon was the very process of galaxy mergers. In the early universe, when galaxies were smaller and more numerous, there were frequent interactions and collisions between them. However, as the universe expanded and matured, such collisions became less frequent, resulting in fewer new galaxies. Another factor is the changing influence of dark matter halos. In the early universe, halos were smaller and more concentrated, favoring the collapse of gas and the formation of new stars and galaxies. As the universe expanded, it became larger and more diffuse, making it harder for the gas to cool and condense into new formations. The large-scale structure of the universe, often referred to as the cosmic web, also plays a notable role in this process. Galaxies are not randomly distributed, but are arranged along huge threads of dark matter that stretch across the cosmos, connecting galaxy clusters. Along these threads, gas flows into them, fueling the star formation process. However, in the present epoch, most of the gas has already been consumed or trapped in larger and more stable structures, which also leads to a decrease in the rate of new formation. However, despite all that we've just said, there are rare cases that violate this trend. One such example is the dwarf irregular galaxy known as Zwicky 18. Located about 45 million light-years away, this galaxy is notable for having a relatively recent burst of star formation. Unlike most, Zwicky 18 began its first major burst of star formation only about 500 million years ago, well after the period when most galaxies in the universe were fully formed. The slow evolution of Zwicky 18 represents an intriguing case in the study of galaxy formation. Its star-forming regions are characterized by intense ultraviolet emission and stellar winds from young massive stars. The presence of these young stars, combined with the overall low metallicity, suggests that Zwicky 18 did not undergo the same evolutionary processes as most other galaxies. This late bloom may provide clues to the conditions favoring delayed star formation and raise the question of the role of environmental factors, such as nearby galaxy interactions in triggering or suppressing star formation. Another notable case is a galaxy with a rather unwieldy name of HSC J1631+4426, discovered through observations with a Subaru telescope. Located 430 million light-years away, this specimen is not only young, but also holds the record for the lowest observed oxygen content. The low oxygen content indicates that the galaxy is in the very early stages of its formation and has only recently begun to convert primordial hydrogen and helium into heavier elements through stellar nucleosynthesis. The galaxy's small size, about 0.8 million solar masses, comparable to a star cluster in our Milky Way, further emphasizes its youth. The fact that such a young and small specimen exists so late in the history of the universe is surprising, given that in the early universe, the conditions for galaxy formation were much more favorable. And given that the expansion of the universe continues to accelerate, making conditions for the formation of new galaxies more and more impossible, such findings become quite extraordinary. At the same time, star formation is a continuous process that continues even in ancient galaxies. And star clusters such as the Pleiades provide clear evidence of this ongoing activity. The Pleiades, often referred to as the Seven Sisters, is a young open star cluster located just 448 light-years from Earth. Despite the age of the Milky Way galaxy being over 13 billion years old, the Pleiades cluster is a relative newcomer, having formed only about 100 million years ago. This indicates that even in such a mature galaxy as ours, there are still regions of active star formation. The formation of star clusters like the Pleiades usually occurs in regions of galaxies where there's a high concentration of gas and dust. These molecular clouds collapse under their gravity, giving birth to new stars. In the case of the Pleiades, the stars of the cluster are still relatively young and hot, and they emit bright blue light, making the cluster visible to the naked eye. Such star clusters are not unique to our galaxy. In neighboring galaxies, such as the Large Magellanic Cloud, abbreviated LMC, star formation is also ongoing. The LMC, a companion galaxy to the Milky Way, contains the oldest known stars as well as regions where new ones are still forming. One such ancient star, LMC 119, that was only discovered this year, is believed by scientists to be about 13 billion years old. This discovery highlights the remarkable longevity of some stars and suggests the conditions for star formation are still not fully understood by us. These star-forming regions are not just remnants of the past, but a critical factor in the future evolution of galaxies. As new stars form, they contribute to ongoing dynamical processes in their host galaxies, affecting everything from the formation of planetary systems to the distribution of elements necessary for life. While star formation continues in some regions of galaxies, like the Milky Way, A significant factor affecting the overall evolution of these galaxies is the presence of the previously mentioned dark matter halos. These halos extend far beyond the visible edges of galaxies and play a crucial role in their formation and structure. As we know, dark matter has a significant gravitational influence on galaxies. This influence is most evident in the way galaxies rotate. Observations have shown that the outer regions of spiral galaxies, including the Milky Way, rotate much faster than would be expected with only visible matter. This discrepancy suggests the presence of a massive invisible component forming a spherical halo around the galaxy. The dark matter halo not only stabilizes galaxies, but also affects their ability to form new stars, and, consequently, new galaxies. In the early universe, dark matter halos provided the gravitational wells necessary for the collapse of gas and the formation of the first galaxies. Over time, however, these halos grew in size and became more diffuse, preventing the formation of new galaxies. The expanding halos, with their enormous gravitational influence, can prevent the gas from cooling and condensing into new stars, effectively suppressing the birth of new galaxies in the current epoch. These dynamics create a delicate balance in the cosmos, where dark matter both promotes and inhibits the growth of cosmic structures. According to scientists, the presence of such halos is one of the key reasons why we see fewer new galaxies forming today compared to the early universe, marking a significant shift in cosmic evolution. Understanding the formation and evolution of galaxies remains one of the most serious challenges of cosmology. Despite significant progress, debates about the fundamental processes that shape the universe are still ongoing. One of the key debates concerns the formation of structures in the cosmos, whether it occurs according to the top-down or bottom-up approach. According to the top-down model, large cosmic structures form first, and then they break up into smaller galaxies and clusters. According to this model, the largest galaxies and galaxy clusters appeared at the very beginning of the universe's history, and smaller structures were formed as these large structures decayed. In contrast, the bottom-up model suggests that small structures formed first, and tiny proto-galaxies and star clusters eventually merged to form larger galaxies and clusters. This theory is consistent with the observed hierarchical nature of the universe, where small objects merge into more complex and massive systems over billions of years. Although these models provide a foundation for understanding galaxy formation, recent observations have revealed complexities that challenge both theories. For example, the discovery of ancient massive galaxies in the early universe suggests a more subtle interaction between these processes, perhaps indicating that the true nature of cosmic evolution is a combination of both scenarios. Nevertheless, the search for and understanding of new galaxies continues to drive astronomical research. JWST has already opened new windows into the distant universe, allowing astronomers to peer into an era when galaxies were just forming. One of the most intriguing questions is whether new galaxies are still forming today. While the early universe was fertile ground for galaxies to form, today's cosmic landscape presents a different picture. As the universe expands and dark energy accelerates this expansion, conditions suitable for galaxy formation become increasingly rare. Future astronomical missions are poised to push the boundaries of our knowledge even further. Instruments such as the Vera C. Rubin Observatory and the European Space Agency's Euclid mission will shortly carry out deep space surveys that are likely to reveal new galaxies that have eluded previous observations. These missions are aimed not only at discovering new galaxies, but also at unlocking the mysteries of dark matter, dark energy, and the overarching structure of the universe. History of the universe is far from complete. As we continue to explore the cosmos, discoveries change our understanding and raise new questions. Each glimpse into the distant past brings us closer to unraveling the mysteries of the universe's formation and fate. Stay tuned for more discoveries to come. Imagine a single point, just a speck of light, hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even in this case, you've barely touched the surface. Beyond our Earth, beyond our Sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans. But how do we comprehend a structure that stretches billions of light years? Today, we're on a journey to explore these galactic threads, the sinews and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong, each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now, imagine a web woven not by spiders, but by the very fabric of space and time itself. A web that links galaxies, star clusters, and dark matter into a complex web. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network this structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now see. One of the most impressive examples of a galactic filament is the Great Wall of Hercules' northern corona. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution? Or is there a grander design at work here? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green, suspended in the vastness of space. A planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field, all these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, It's just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around the Earth. Yet despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason. It has life. It's the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the sun, the blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images, the reason life exists on Earth. But in the context of the cosmic web, the sun is just one node, a lone star among countless others. Close to the sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our sun is located in the Orion sleeve of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special, just one of about 400 billion stars. In the great expanse of the cosmic web, stars like our sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So what powers this celestial beacon? The answer is nuclear fusion. Deep in the sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life. It drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the sun. Although the sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to the massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness, and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. They're small, cold stars, also called M-type stars. Often less than half the mass of our sun, they make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal. They turn hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the sun and can be 1,000,000 times brighter. Yet they live fast, die young, often in spectacular supernova explosions. O-type stars dramatically end their lives. They collapse under their own gravity and then explode as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic web, linking different regions of a galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out, stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, getting denser and hotter until nuclear fusion ignites. A new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our sun is now. But even stars like our sun must face change. In about 5 billion years, the sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the final fate of the star. Depending on its mass, the star will meet one of several ends. Stars with less mass, such as our sun, will shed their outer layers, leaving behind a white dwarf. More massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death agonies of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? What are the threads that weave the complex fabric of the universe? The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies and often span millions of light years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static. They are in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters, and, by extension, the cosmic web. But clusters are not the end of the story. They often cluster together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies, forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy that stitch together the fabric of the universe. These hypothetical one-dimensional defects in space-time could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to structures of unfathomable scale. Superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy, past our local group of galaxies, and even beyond our local Virgo supergroup. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies. And yet, what we can see represents less than 5% of the universe. Standing over the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web. Yet, it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light years away, we become not just spectators, but active participants in this cosmic journey. And each new discovery is a step towards the answer to the eternal question that prompts all of us to ponder: what other mysteries does the universe hold that we have yet to unravel?